Assalamualaikum and hello everyone. We are from group 4. Today we are going to present about experiment 5, bending moment. Our group consists of 4 members, which are Muhammad Afan, Muhammad Arsi, Muhammad Daniel Haikal, and me myself, Muhammad Alafis. So I will start present the first topic, which is the abstract. The purpose of this experiment is to measure the bending moment of material at a normal section of loaded beam. The experiment is conducted by using an experimental beam that is divided into two parts, which are connected by a joint which form a frictionless hinge where there is moment of resistance that is generated by an underslung spring balance. Load is induced onto the beam by placing three load hangers to pass on the beam. When load is placed into the beam will start to bend. Every time load is changed for a new placement, the spring balance is tuned to align both parts of the beam. Then the value of net force for the load is taken by reading the spring balance. In this experiment, the steps will be repeated for different placement of load hangers on the beam with different loads. By using all the data collected from the experiment, the bending moment for each load placement is calculated. Graphs of bending moment against distance are drawn to compare the experimental and theoretical values of bending moment. The bending moment is proportional to the load applied on beam. The similarity and difference between the experimental and theory values will be identified and discussed accordingly. Finally, principle of bending moment is relevant to calculate the bending moment despite having small difference between experimental and theoretical values. The difference of values is due to errors occur in the process of conducting this experiment. So, this is the objective of this experiment. The first one is to study the property of material, which is bending moment when subject to different load. Second one is to comprehend the action of moment of resistance in a beam. And the last one is to measure bending moment at a normal section of loaded beam and to check its agreement with the theory. Next part is introduction. A bending moment is the reaction that occurs in a structural element where an external force or moment causes the element to bend. The beam is the most basic or simplest structural feature subjected to bending moments. The bending force will cause the object to turn at a certain point if the object is not well restrained. The internal reaction loads can be resolved into a resultant force and a resultant couple in the cross section of the beam structure. For balance, the moment produced by external force should be balanced by the intermediate force. Next, I will pass the theory part to Afan.
Okay, so my name is Muhammad Afan. So I will cover for theory and procedure. So this experiment 5 we're dealing with bending moment experiment, which is it is involve beam in this experiment. So what is beam? Beam is actually a structural element which designed to bear with high load of structure and other external load. There are various types of beam, which are cantilever beam, sample supported beam, and overhanging beam. So when a beam is loaded by forces or couples or the internal stress, so internal stress and strain are created. In order to determine the stress and strain, the internal force and internal couples that act on cross section of the beam should be determined. So as we can see in figure 1, So that is the simple sample of load, sample of beam with P as internal P, RA and RS is external load, and there are two type of beam, which is part A and part B. Next. So in this experiment, we consider P as we can see in the diagram or in the figure 2 at left hand side or figure B. We consider the force P act vertically in the cantilever beam. So now we imagine that the beam is cut through at the cross section at X, which is the blue rectangle, blue box. For the left hand part, which is part A, the shear force Qx and bending moment are assumed to be positive in the direction as shown in figure 2. Figure 2b, figure 2b and figure 2c. The positive direction is vice versa if the right hand part, which is part B of the beam, is considered. So for vertical equilibrium of part A, there must be a shear force, which is Qx, and acting as shown in figure 1b, and it is equal to force negative RA. For vertical equilibrium of part B, the shear force Qx evidently act as shown and has the value of P minus force RP. Next slide. So this is the sample of beam before we cut into two part, which is part A and part B. For the diagram in figure above, we have diagram A, which we don't cut into two part, and diagram B we have cut into two part, and diagram C we cut into two part, and we want to consider the moment of the two part. So for equilibrium part A, the moment is equals to force RA. We times with the direction of XA, and the part B or the moment of part B, MB equals to the force of RB times with the direction of XB. We minus with external force B times with the direction of B minus direction of L or length of L. So thus we got the overall equals to mx equals to RA times XA for moment of this diagram.
Hello there, my name is Muhammad Daniel Haikal, matric number A19ET0124. We'll be explaining about two parts for experiment 5, which are apparatus and the calculations part. So let's start from apparatus parts first. So from the left, we could see that there's the experimental beams for part 1 and part 2, the load hangers which are actually hanging onto those experimental beams, and also the loads. So on the right, there would be the spirit level, which we would be needing to actually balance the spirit level, be balancing the beams between each other, and also the spring balance.
So next is the methodology or the procedure of the experiment. First procedure is the beam was set up as in figure 3, where the load hanger for P1 is 200 millimeter for P2, and P3 is 300 millimeter for force 2. Second procedure is the two parts of the beam were aligned using the adjustment on the spring by turning the spring balance until the bubble in the balance is at the center. The third one is when the bubble is at the center, so the initial reading from the spring gauge was taken, and recorded in the table 1 as in the result. For 0 root column for all P1, P2 and P3. Next step is the reading just now will be the balance reading, and the net force for load was 0 as new load was applied on the load hanger yet. And next step is what required in table A1. 10 Newton weight was applied at P1, and the spring balance was realigned, and the reading was recorded. So the new reading was the effect of applying the 10 Newton weight on the beam, and would be a balance reading while the net force was the difference between this reading at 10 Newton with the reading at 0 Newton earlier of the experiment. So I think that's all from my part. I will pass to the next presenter. Thank you.
Now we'll be going into results and calculation parts. For these parts, it's going to be divided into 3 parts, which are part 1, part 2A, and also part 2B. So for the first part, we'll be calculating the bending moment for load when it's 10 at P1, P2, P3, and also when the load is 20 at P1, P2, and P3. So these are the results for part 1. For part 1, when the load is 10, we can get that P1, P2, and P3 will be 600, 1800, 900, and with their own respective theoretical values. And also the load for 20 as 1200, 3600, and 1800. So for us to actually calculate for part 1, for when the value is when the value of weight 1 is 10, the bending moment at point C, which is MC is equals to net force times with 150. So from there we can actually get MC equals to 24 minus 20 times with 150. Then from there we can get the bending moment, calculated bending moment at 600. So from there we will be calculating about the moment at point B, which is MB. So we would assume clockwise as positive equals to 0. RA is equals to 900, which from the picture we can actually see that the from point A to B is actually 900 millimeters, and then minus, since this is going to be counterclockwise, it will be negative 10 times with 900 minus 100, since the distance between for P1 is actually from point B, it will be 900 minus 100. So from there we can actually get RA. RA would be 8.889 Newton. So from there we could actually also get MC in theoretically, which will be around 666.67. So the same goes as for P2. It's actually the same way for how to calculate the bending moment. It's also the same way actually to calculate moment, the bending moment theoretically. You can also get it there. So for P3 it's also the same. There's no difference also. So next slide. So these are the results for part 2A. So for this part, we'll actually be setting that the P2 is actually equals to 5, and for the second one will be P1 equals to P3, which is equals to 10. So that means P1 P3 will be the same, and P2 is equals to 5. So the value would be as follows: 18,000, 25.7 net force, bending moment which is 1050. Bending moment theoretically it's 1000. Balance reading it's 36. Net force will be 18. Bending moment will be at 2700. And the bending moment theoretically for the last one would be 2668. So how to actually calculate for part 2a? Well, for when the load is actually 5 Newton at P2, the bending moment, as we know, calculated from before, is actually still the same. So it's just 25 minus 18 times with 150. So we will be getting 1050 Newton per Newton millimeter. So from there, we'll be finding about the moment at point A. Then from there, moment from point A, clockwise, positive, then we'll be getting RB. So RB will be 1.67. Then from there, we can actually get RA, which is 3.33. So there, we can actually get the bending moment at C theoretically, which is RA times with 300. We'll be getting around 1000 Newton millimeter. So the other one would also be the same about finding the bending moment, be also the same. But the only difference would be at finding at calculating RB, since we have that value of P1, P2, and also P3. Since it's all different for this part, so we need to calculate each of it. So for instance, for load P1, the distance between for it from A would be 100 millimeters, as you can see from the picture. Then 300 for P2, and P3 will be 600. So from there we can actually get RB 9.44. Then we can actually calculate RA, since all of the things that we need are there. So RA will be 15.56. Then from there we can actually get MC theoretically would be 2668. So this is the last one for part 2b. So as it follows, it's also almost the same as before, but this time we'll be calculating P1 equals to 5, P3 equals to 12, P1 equals to 5, P2 10, and P3 equals to 2. So as it follows, and bending moment for P1 5 and P3 12 will be 1500. Theoretically, it will be 1933.33. For P1 5, P2 10, and P3 2, it will be bending moment at 2400. And the bending moment theoretically would be 2600. So how to calculate this? Well, it's almost same as before, still the same. And I think that's all for the results and calculation parts. So thank you.
My name is Muhammad RC bin Abdul, and I will continue with discussion and conclusion part. For the discussion, when the load was doubled in part 1 of the experiment, did the bending moment double? Explain. Okay. When the load is increased, the bending moment also increased. Based on the calculation data from calculation part 1 that Haikal just present, the value of moment is directly proportional to the force that being applied. When the stress double, the bending moment will increase double the original value. The bending moment will double when the load double. This shown at the calculation. There is a slightly error in the value obtained due to some error that occurred during the experiment. But the theoretical value still show that the bending moment still double when the load double. For an example, when P1 is 10 Newton and the bending moment is 600 Newton per millimeter compared to 666.67 Newton millimeter. When the load doubled, there is 133.33 Newton millimeter difference between the theoretical bending moment and actual bending moment obtained from the experiment. This might be occur to error during the experiment. Okay, for the data below, we can see that the bending moment double when the load double. As you all can see, P1 600 at the load 10. When the load is 20, it become 1200. For P2, for the 10 load, 10 Newton load, 1800, and the 20 Newton load, 3600. And for the P3, 10 Newton load, 900, and 20 Newton load is 1800. Okay, for discussion number 2, compare the average figure for each of the experiment by using the bending moment value double from experiment and theoretical. Use either a ratio or percentage error. For this part, I use percentage error, which the formula is theoretical minus experimental data divided by theoretical, and then multiply with 100%. Okay, for P1 we got percentage error 10, P2 55, P3 10 for 10 Newton load. It goes the same for 20 Newton load, which is P1 is 10%, P2 is 55%, and P3 is 10%. This is the calculation. Just use the formula percentage error equal to theoretical minus by actual, which is experimental value, multiply with 100%, and then we got the data. Okay, for load 10 Newton, the average percentage error is 25. For 20 Newton loads, the average percentage error is also 25. This is the percentage error for part 2A and 2B. For 2A, P2 equal to 5, the percentage error is 5 when P1, P3 equal to 10 Newton, P2 equal to 5 Newton. The percentage error is 1.25. Okay, for part 2B, P1 equal to 5 Newton, P3 equal to 12 Newton. The percentage error is 22, and for P1 equal to 5 Newton, P2 10 Newton, P3 equal to 2 Newton. The percentage error is 7.7%. Okay, this is the calculation for part 2A, part 2B. Just use the same formula. Okay, the average percentage error value for 10 Newton and 20 Newton loads are slightly similar. This is due to some error that occur during the experiment process, which is the scale of spring balance is not precise enough to get the accurate data. The hanger might be moving during the adjustment of the beam was made. Parallax error when the reading taken. To make sure this is not happen, just use a precise scale of spring balance to read the reading. Make sure the hanger statistic during the adjustment of the beam. And then read the measurement with a perpendicular eye with the scale to get an accurate data. Okay, we move to this conclusion part. Based on the experiment result in part 1, basically when the load is double, the bending moment become double on the beam. Basically the value or bending moment verifying the theory in part 1 and also part 2. The percentage error are small, although there is a deviation between theoretical experiment result explained for the 55% and 22% percentage error. For that, the theory has been verified, although there is some error occur. Okay, that's all from us. Thank you.